In the first triangle video, we talked about ideas that were true for all triangles. Now we're going to limit things and just begin with two special categories of triangles: isosceles triangles and equilateral triangles. An isosceles triangle is one in which two sides are equal. For example, here we have an isosceles triangle, ABC. Such a triangle would also have equal angles, opposites of the sides. So this angle here equals this angle here. In fact, Euclid's remarkable theorem about these is a two-way theorem. In other words, if we know that the two sides are equal, then we can conclude that the two angles are equal. If we know that the two angles are equal, then we can conclude that the two sides are equal. So it's important to know that the logic goes both ways there. Could an isosceles triangle have a right angle? Could it have an obtuse angle? Absolutely. So for example, DEF is a right isosceles triangle, and JKL is an obtuse isosceles triangle. And in fact, we could find the other angles in each case. And so we could have one large angle and then two small equal angles. An equilateral triangle has three equal sides and three equal angles. All the angles have to be 60 degrees. So this is an equilateral triangle. Is an equilateral triangle also an isosceles triangle? Technically, yes. Technically, the definition of an isosceles triangle is a triangle with two or more equal sides. So equilateral is included. In all likelihood, the test will not ask you directly about that distinction. They will not ask you, is an equilateral triangle isosceles or not? That's not the type of thing they're going to ask. But you need to know that every special fact about isosceles triangles automatically applies to equilateral triangles as well. That you need to know. Now we will return for a moment to all triangles. The area of a triangle is how much space the triangle takes up. If the units used, the area, of course, is measured in square units, such as square inch or centimeters squared, that sort of thing. You may remember the formula, area equals 1/2 base times height, where b is the base and h is the height. But those problematic terms need to be clarified. What exactly is the base of a triangle? Naive students will say the bottom side, but that is not the whole answer. In fact, that's kind of a misleading way to think about it. Part of the problem is that some textbooks often insist on representing every triangle in the world with a horizontal line on the bottom. And this overrepresentation of one orientation misleads students into mistakenly thinking that every triangle automatically comes with a horizontal bottom side. And that's simply not the case. So here's a triangle, a perfectly good triangle. There's no horizontal line in this triangle. What exactly is the base? Well, it turns out base has nothing to do with being horizontal. In fact, in any triangle, any of the three sides could be the base. There are actually three different bases, and we call it a base when we use that side to find the area. So AB could be the base, AC could be the base, or BC could be the base. Any three of those could be the base. That's important idea number one. Now, what's exactly the height of the triangle? Just as students naively assume that the base is horizontal, they naively assume that the height is vertical. Neither one of those is necessarily true. In fact, h is a length of a segment called the altitude. So approximately, the altitude is a segment from a vertex to an opposite side that is perpendicular to that side. And so, in other words, whichever side we're using, that side's going to be the base, and then the altitude is perpendicular to the base, and it goes through the opposite vertex. Just as any side can be the base, we can draw an altitude from any vertex to any opposite side. So here's the same triangle. In the first triangle, we're using AC as the base, and we draw altitude BD. In the second triangle, we're using BC as the base, and we draw altitude AE. In the third triangle, we use AB as the base, and we draw altitude CF. So we have three different ways to pick the base, three different possible altitudes, and hence three different ways to find the area. Now here we're not given any numbers. presumably in a problem you would only be given certain numbers, but you have at least the possibility of finding the area in these three different ways, depending on which numbers you were given. Now I'll point out this rough definition of an altitude is fine in triangles in which all three angles are acute. But think about an obtuse triangle. There's no way to draw a segment from point P to line M. Any segment that's going to go through line M is not going to be perpendicular. There's no way to draw a perpendicular line that goes through P and intersects MN. So what we actually have to do here is we have to extend the line. We have to extend NM, extend that segment out along a line, and then we can draw a segment from P that is perpendicular to that extended segment. So here, if MN is the base, then PR is the altitude. And we can find the area base times altitude. And of course, we could also draw the altitude from N to MP, or we could extend segment NP and draw altitude MT. And this gives us two more ways to find the area of the same triangle. And of course, if we actually had numbers, of course, all three ways of calculating the area would lead to the same area, because a triangle only has one area, no matter which way we calculate it. Notice that in right triangles, two of the altitudes would be legs, the sides that meet at the right angle. If one leg is the base, the other leg is the height, and then either way, the area equals 1/2 times the product of the legs. So area equals 1/2 of AC times BC. Students sometimes worry about how to find the length of the altitude, how to find the height. The test will not simply give you the three sides and expect you to find an altitude or expect you to find the area. That is something you could do with trigonometry, but that is well beyond what the test is going to ask. One thing to keep in mind is the altitude always forms smaller right triangles within any triangle. This means that sometimes we might use the Pythagorean theorem or another right triangle fact to find an altitude. We'll discuss that more in the next video. Here's a practice problem. Pause the video and then we'll talk about this. Okay. In the diagram, two altitudes are drawn. Find the length of G. And so GF. So this is very interesting. We've extended line FH and then drawn altitude GX to it. And so GX is an altitude and FH is a base. We also have extended line GF and drawn altitude HY. And so HY is an altitude and GF is a base. So we have two different ways of figuring out the area. First of all, we could figure out the area using FH as the base and GX as the height. And we have numbers for both of those. So this is going to be 1/2 14 times 6. I'm just going to leave that in unmultiplied form for a moment. But notice I could also find it in a completely different way using the other altitude and the other base. So now I'm going to use the base GF and the altitude HY. So this is another way to figure out. Here I know HY is 7. But I don't know FG or GF. In fact, that's exactly what I need to find. But now notice that we have two different expressions for area, but of course these have to be equal, because if the triangle only has one area, and so any way of calculating it should lead to the same number. So we can actually set those two equal. We can cancel the 1/2, divide by 7, and then we get FG equals 2 times 6, which is 12. And that's the answer. Now we're going to talk about 4 kinds of lines in a triangle. You will not need to know these names, but you will need to keep these ideas straight. You will need to keep straight what you can and can't conclude. The first line that we've already talked about is the altitude. And this goes through the vertex and is perpendicular either to the opposite side or at least perpendicular to the segment extending the opposite side. That's an altitude. Always makes a right angle. Obviously, the point where the altitude intersects the opposite side usually isn't the midpoint. So here S does not happen to be the midpoint. It's just some random point on segment PR. The second special line is the perpendicular bisector. So this also makes a right angle, but this bisects a line at its midpoint. And notice that this one doesn't necessarily go through the opposite vertex at all. So the green line is the perpendicular bisector, and this is not even pretending to try to go through Q. It just misses Q entirely. But M is the midpoint, and so it is dividing PR in half. And one thing that's special about a perpendicular bisector, every point on there is equidistant from point P and point R. The third special line from a vertex goes from the vertex to the midpoint of the opposite side. And this is called the median. You don't need to know that word. But the big idea here is that in a general triangle, the median divides the opposite side in half, but it does not necessarily divide the angle in half. And so we definitely know that PM equals MR because M is a median, but in general, it's going to be true that those two angles at Q are not equal to each other. So that's really important to know. If you're told that something intersects a midpoint, you cannot simply conclude that the two angles are equal also. Conversely, the fourth special line is called an angle bisector. The job of an angle bisector is to cut the angle in half. So it bisects the angle, divides the angle in half, but usually it doesn't divide the opposite side in half. And so here we can see quite clearly V is certainly not the midpoint of PR. So the two angles at Q are now equal, but clearly PV and VR are two completely different lengths. You have to appreciate what is and isn't true in most triangles in order to appreciate the special thing that happens only in an isosceles triangle. The line down the middle of an isosceles triangle from the vertex to the midpoint of the base plays all four of these roles at once. So in other words, point T is the midpoint of the base. That means that GT is perpendicular to the base at F, and it means that GT bisects the angle at G's. And so we know that we get equal angles up here. We know that these two segments are equal. We know that all of these qualities are true all at once because it's an isosceles triangle. And that coincidence of those four lines all playing the same role only happens in an isosceles triangle. The four special lines are four different lines in most ordinary triangles, and certainly in all non-isosceles triangles. And so we get information that one segment is playing more than one role. It's both perpendicular and an angle bisector, for example. That's enough to prove that the triangle is isosceles. The midline in an isosceles triangle is a line of symmetry, so it divides the bigger triangle into two congruent right triangles. Of course, all these triangle facts apply to the equilateral triangle, which is a special case of isosceles. In summary, an isosceles triangle has equal side lengths and opposite equal angles. Equilateral triangle has three equal sides and all 60-degree angles. Area equals 1/2 base times height. The base can be any side, and the altitude is perpendicular to that side. And then we talked about the altitude, the perpendicular bisector, the line from the vertex to the opposite midpoint called the median, and the angle bisector. And these are four completely different lines in most triangles, but the line of symmetry in an isosceles triangle plays all four of those roles at once. And so that is one of the magical qualities of an isosceles triangle.